In this video, we discuss learning outcome number 3 from lesson 10.1, which is about conducting a hypothesis test to determine whether there's a linear correlation between two variables using the critical value method. So we'll start by discussing the null and alternative hypotheses for claims about correlation. Whenever we're conducting a formal hypothesis test to determine whether we have evidence of a correlation, we're going to use the following null and alternative hypotheses. You want to remember that the lowercase rho is the linear correlation coefficient of the population. So that in mind, the null hypothesis is always that there is no linear correlation, or in other words, that population linear correlation coefficient is equal to 0. Now, if that population linear correlation coefficient is non-zero, that would be our alternative hypothesis, and that would provide evidence of some linear correlation between the two variables. Now, rarely, but occasionally, we may use the following alternative hypotheses instead. Rather than saying that we have evidence of a correlation, we might be interested in whether we have a positive correlation or a negative correlation. Our claim might be that there's a positive correlation between two variables. In that case, we would use this alternative hypothesis. And of course, our claim might be that there is a negative correlation between two variables. In that case, the alternative would be that that linear correlation coefficient for the population rho is less than 0, which makes it a negative value. Okay, so after we've stated our null and alternative hypotheses, which are usually that rho is equal to 0 and rho is not equal to 0, then we need to check the requirements for testing a claim of linear correlation between two variables. The first requirement is that the sample of paired data has to be a simple random sample of quantitative data. If the data are not randomly selected, we could come to some conclusion, but that conclusion is only valid if we started with a simple random sample of quantitative data. Now, the second requirement is that when we look at the scatter plot of our XY pairs, we must confirm that those points approximate a straight line pattern. If they don't approximate a straight line pattern, it's not appropriate to even test the claim of a linear correlation between the variables, because we can look at the data and see that there's not a linear relationship there. And third, we need to remove outliers if we know them to be errors. And if we see that there are some outliers, we might calculate R with and without the outliers, and then determine what to do based on the results of the two R values that we find with and without outliers. And this is because the value of R is strongly affected by the presence of outliers. Remember, R is calculated by taking the z-score of the x value and the z-score of the corresponding y value and multiplying those together and then adding them for all of the possible xy pairs in our sample and then dividing by one less than the sample size. When we do that, outliers are going to correspond to z-scores that are far from 0. So those are going to be values of x and values of y that are much higher than the mean or much lower than the mean. And those will strongly affect the value of R. And if we don't want that, if that outlier is not representative of our data set in general, we might want to take that out. Now, those last two requirements are what is being used to verify one quality. We're trying to verify with requirements 2 and 3 that the XY data have a bivariate normal distribution. And what that means is that when one of the variables fixed, the other variable has a normal distribution. It's normally distributed for that particular value of the other variable. And that's very hard to verify. So instead of verifying that the data have a bivariate normal distribution, we're saying that if 2 is satisfied and if 3 is satisfied, if we have very few outliers and we have approximately a straight line pattern, we can assume that the XY data have a bivariate normal distribution. Okay, so once we know that the requirements are met, testing a claim using the critical value method is actually really simple. we don't actually find critical values of a test statistic T here. We actually have a table of critical values for our sample statistic R. We're going to use table A5, which lists critical values for alpha equals 0.05 and alpha equals 0.01 for different sample sizes. Now, when you're using table A5, you want to consider the critical values from that table or from technology. So if you use a TI-83 or 84, or you use Excel or some other type of technology like StatDisk or Minitab or StatCrunch, one of those, if you're using those, you want to consider the critical values to be both positive and negative. And this is because of that alternative hypothesis. When we're trying to test whether or not there is a correlation between the variables, the alternative hypothesis is that there is a correlation, or in other words, rho is not equal to 0. So that means we're going to have critical values on the left and on the right. So that means we'll have positive and negative critical values. Now, we'll have evidence of a correlation if the absolute value of our linear correlation coefficient R is greater than the critical value. That means it's farther from the mean than the critical value is. It's farther away from rho equals 0 than that critical value is. If the absolute value of R is greater than the critical value, we will conclude that there's sufficient evidence to support the claim of a linear correlation. If the absolute value of our computed value of R from our data is less than the critical value, we'll conclude that there's not sufficient evidence to support the claim of a linear correlation. Now, all of this is very similar to what we did before when we talked about hypothesis testing in chapters 8 and 9. This time, we're not talking too much about the distribution of this sample statistic R, but it has a distribution. It turns out that if R is relatively low, the distribution of R is approximately normally distributed, but the higher R gets, the more skewed the distribution of R becomes, or the higher rho gets, actually, I think it is, the more skewed the distribution of R becomes. So we're not actually going to look at that distribution, but we are going to look at a line like this, a line segment like this. The R values range between -1 and 1, and we're going to think of having that rho equals 0 in the middle here. Now, if our R values are between these two critical values, between the negative critical value and the positive critical value, we're going to say that the R value is not significantly high or significantly low, given that the null hypothesis is true, or given that there is not actually a linear correlation between the two variables. That particular value of R could easily happen due to chance, given that there's no correlation. So if R is between the critical values, we're going to say that there's no correlation. If the absolute value of R is greater than the critical values, so that value, absolute value of R is between this positive critical value and 1, in that case, we're going to say there is evidence of a correlation. So if the test or the sample statistic R is in this range or in this range, we'll say we have a correlation. And if it's in between the two critical values, we'll say that there is not evidence of a correlation. So this is actually pretty simple. We just need to check the requirements, compute our value of R. Usually we use technology for that. We use table A5 to find the critical values, and then we compare our R value to the critical values in the table and use that inequality involving the absolute value of R and the absolute value of critical values in order to make our final decision. So we're still dealing with that Nobel laureate data. We've got amount of chocolate consumed in certain countries, and I don't remember the units for that, and then the number of Nobel laureates from those countries. And it turns out that if we have 23 pairs of data, which are going to be shown on the next slide, the R value, the linear correlation coefficient for that sample of 23 pairs of data, is approximately 0.801. If we use a significance level of 0.05, that's our alpha. The question is Is there sufficient evidence to support a claim that there's a linear correlation between chocolate consumption and the number of Nobel laureates in a particular country? Well, we have this data. These are the 23 pairs of data. Here's how much chocolate was consumed in some number of units and the number of Nobel laureates. And now obviously you don't have 24.3 Nobel laureates, so there are some units associated with this number of Nobel laureates as well. The question is, are these two variables correlated? Well, in order to determine whether the two variables are correlated, we would check to see if we have a simple random sample of quantitative data. Well, we have quantitative data, but we're not really sure that it's a simple random sample, because how can we know that those 23 countries on our list were a simple random sample of countries around the globe? So since that is questionable, everything that we do after this point may not be valid. But we're going to assume that it's valid. We're going to see what we come up with. But if we don't actually have a simple random sample, none of the analysis that we do really generalizes. So we should be careful about that. Now, the second requirement and the third requirement deal with the scatter plot. So the second requirement was that the scatter plot should show a straight line pattern. If we look at the scatter plot of those 23 pairs of data, this is what we see. And that does show approximately a straight line pattern. We also don't see any outliers. Now, some students say, well, what about that guy? And what about that guy? Well, if I have a line that's going through this data, it's approximately in the middle here. Like that one's not that different than that one. It's not that far out from that one. So I would say that there are no outliers here. Now, after you check those requirements, and then we'll just assume that we have a simple random sample, we could create this scatter plot ourselves using Excel. We can also calculate the linear correlation coefficient R using Excel. So let me show you how to do that. So these are my ordered pairs. These are my 23 pairs of data. I want to find R, I'll type equals Pearson, open parentheses, and then select that first column for my first array and select the second column for my second array and close parentheses, and we get 0.7995. And I get 0.800, not 0.801, but they got a slightly different value. That's okay. We're off by 0.001. Now, if I want to construct a scatter plot, I'll just highlight those two columns, go to Insert, then go over here and then choose Scatter. And I see the same graph that we saw in Excel, or not in Excel, in the slides. So that's how you would do that if you did not have that slide providing that R value for you or coming up with that scatter plot. You could create that scatter plot yourself. Now, if I want to determine whether we have a linear correlation, I would look at table A5 and consider the critical values listed in the table as being both positive and negative, and then draw a graph similar to the one in this figure over here. It says that our critical values are R equals 0.413 and R equals negative 0.413. Those are typically provided by technology. So if you were to enter these 23 pairs of data in your TI-83 calculator, TI-83 or 84 calculator, they would give you these two critical values. Now, table A5 won't give you those values, but we'll get close to that as we're going to see on the next slide. So these are the true critical values that are computed using our data. Now, we could use Excel to compute those critical values, but it's quite involved. And I think table A5 will do just fine for our purposes. So I'm not going to show you how to use Excel to find the critical values, although you can use Excel to find those. I would look up Using Excel to find Pearson critical values, just Google that and you'll find some code that's out there that will tell you exactly how to calculate those R values for particular values of alpha and for particular sample sizes. Okay, so once we have our critical values, which will be provided by technology or we'll look them up in table A5, we compare our R value, which was that 0.801 according to the slide or 0.800 according to Excel. We compare that to the absolute value of the critical value. So 0.8 is obviously greater than 0.413. It's over here. So it's beyond that critical value. Between the two critical values, we have no evidence of a correlation. Beyond the two critical values, we have evidence of a correlation. So since our linear correlation coefficient R is beyond that top critical value, we have evidence of a correlation between the chocolate consumption in a country and the number of Nobel prizes that are won by people in that country, the number of Nobel laureates. Now, I love this picture of a Nobel Prize. If you click on it, you can find the original source for this. But I love it because it's a Nobel Prize, but it also kind of looks like it's like a gold, like foil covered chocolate. And it makes you wonder, because this question is about chocolates and Nobel Prizes. And you're like, is there any chocolate in there? There's not. It's just a Nobel Prize. But anyway, just being silly. But that picture reminds me of this data set. So we have evidence of a correlation between chocolate consumption and the number of Nobel laureates in a particular country. Now, if I wanted to use table A5 to do this, I would go to table A5, and remember I had 23 ordered pairs. And all this time I've been saying table A5, it's table A6, not table A5. I'm going to have to change my slides. But then you'll go to N over here, that's the number of ordered pairs, and you'll look for the sample size that you have. Now your sample size may not be in here. We've got sample size of 20 and a sample size of 25. So our sample size of 23 is in between these two sample sizes. Now in this first column, these are critical values. These are just the positive critical values corresponding to alpha equals 0.05. These are the positive critical values corresponding to alpha equals 0.01. But these are the ones for the alpha that we have, 0.05. Now, our sample size is 23. So that means our critical values are somewhere in between this plus or minus 3.96 and the plus or minus 0.444. Now, for our purposes, you always want to round down, assume that your sample size is smaller than it actually is, and then use this critical value. Use the larger one here. That is going to make your test a little bit more conservative. You're going to be a little bit less likely to reject the null hypothesis. But the true critical value is actually a number between 20 and 25 over there. So we don't have n equals 23 in the table, so we're going to round down and use the critical values of plus and minus 0.444. And then we could also use a table A5 to infer that the true critical value is between that 0.396 and 0.444. We just don't know what value it is in between this 0.396 and 0.444. So we'll choose the larger one, choose the one that's associated with the smaller sample size. Then we're going to compare the computed value of our linear correlation coefficient, which is approximately 0.801, to the critical values of 0.444. So if the absolute value of our R value was between negative 0.444 and positive 0.444, we would say that there's no evidence, there's not sufficient evidence of a linear correlation between the two variables. But if our R value is beyond that, if it's closer to 1 than those values or closer to negative 1 than those values, then that is sufficient evidence of a linear correlation. Remember, R equals positive 1 is a perfect linear correlation, where the slope of the line that passes through those XY pairs is positive. When R is equal to -1, that is a perfect linear correlation. So that means all of our XY pairs lie on a line. But if R is -1, that just means they lie on a line with a negative slope rather than a line with a positive slope. So if R is close to 1 or close to -1, that's evidence of a linear correlation. And you might say, how close does it have to be to 1 for us to say that there's sufficient evidence of a correlation? Well, it has to be closer to 1 than these critical values. Closer to 1 or closer to -1 than the critical values, which is why we look at the absolute value. Since that 0.801 is greater than 0.444, we have sufficient evidence of a correlation between the variables. Or in other words, in terms of the original claim, there's sufficient evidence to support the claim of a linear correlation between chocolate consumption and the number of Nobel laureates in different countries. Now, that does not imply a cause and effect relationship. Consuming chocolate does not cause you to win Nobel Prizes, and winning a Nobel Prize does not make you want to consume chocolate. And all the people in your country, the rest of the people in your country don't want to consume more chocolate just because you won. I mean, maybe we all want to celebrate, but that's not what this suggests. This just says that one variable can be used to predict the other, because as chocolate consumption goes up, so do Nobel laureates, the number of Nobel laureates go up, and vice versa. So that is using the critical value method to test the hypothesis of a correlation between variables.